All right, so let's get started. We're gonna make a grid, and I'm just gonna move it in space. We're gonna keep it facing the z-axis because it would be really helpful for just to keep it, you know, easy to do. Now, in production, if it's angled, you would want to, I mean, there's multiple ways you could do it. You could construct your pieces down here at origin and then copy the points, extract the orientation of the window, and then use copy to points. That would probably be the easiest way rather than trying to like reverse the orientation every single time. But let's just pretend like this is our window. Let's actually shrink it down a little bit. So instead of also 10 meters, it's pretty ridiculous. Let's say 1 meter by like that. Maybe reduce the number of columns so it's like normalized, something like that. So you can add thickness if you want, but I'm going to prefer to do it on a flat plane. So Boolean fracture, Boolean fracture. You can say trade geometry as surface. Then I'll do just that, treat it as a surface. And then you would just add thickness afterwards, after you fracture. By the way, in case you're wondering, I scaled up this floating gnomon thing with this, hit D, and then down here at the bottom, floating gnomon size. You just, by default, it's like really small, and I don't like that when I hover, see it disappears under the text. So I just increased that to like 2 or maybe 3, so that when I go, I'm in camera mode, it doesn't hide it. I'm gonna start working like that now. So, a fracture. So you can do RBD material fracture, but this breaks so often. So you do glass, you scatter a single point, and look how slow this is. It's ridiculous. They did it, but it was really slow, and it took forever. And these don't even look that good. They're like breaking. And it's airing out. It's not even, it doesn't even look that good. So refresh your viewport. So yes, it works, but you have like no control. There's like, yeah, you can play with these numbers and they don't really make sense what all these things do. So we're going to create our own. So the way we're going to do it is first off, this radial part is actually super, these spokes, we're going to call them spokes, like these part here and here. This part is actually super simple to make. And then the tricky part is going to be the arcs. The tricky part is going to be the arcs. That's going to be difficult. These guys here, like right here, that's going to be difficult. But that is the trickiest part. Other than that, it's pretty straightforward. So the way we're going to do it is basically we're going to have our window and we're going to do this in layers. So the main layer is, let's create one point where, by the way, if you want to snap, just say primitive snapping and then middle click, and then I'll snap to the primitive. I show this in other videos, but like, let's say, okay, we want our point here. Let's say the impact point is here. Now we have that point. This is going to be our impact point. So let's make a null, call it impact point. Now what I like to do, I wrote a very simple script, but if I hit Control Shift O, it'll make a object merge for this and copy it to your clipboard, and you can just paste it. So that way we can reference it down the tree. Copies it to your clipboard and then just removes the node. And then you can just paste it anywhere you want. So I'll show that. We have our grid, we got this impact point, and well, what do we need? We need lines radiating from that impact point. So how do we do that? Well, a circle. We use a circle, we use copy to point, and we're just going to copy from this impact point to here. This is far too big, so let's reduce this, template this, and let's see what happens. Actually, let me make sure, let me confirm this is the correct side to be looking at. It is. Okay, great. This doesn't look correct. Doesn't really matter. So the number of divisions equates to the number of lines we're going to make, and we need this circle later. We're actually going to merge this with the lines to create like a whole piece, but we need this like super small so that the lines emanate outward. And this hole here is going to be like not really super important. It can just be like part of it. It can be so irreducibly small, it doesn't really matter, because the gist of it is copying points from it. So as you probably know, we need normals from the circle, so let's create that. So right now it's at origin, so if we just say b at n equals p, or really normalized p, because we've shrunk it down, so it's not a one-to-one, a unit one. It's not a 1 unit position anymore. We've shrunk it down, so you want to make sure that's normalized. And now the normals are pointing out. So now, when we copy the points a line from here to here, we make sure that this direction is in Z, because of course copies have to be in Z. And now we get our copy. It's okay if it's too long, because actually that's kind of ideal, because you have to make sure it extends the full length, if not more. It needs to extend a little bit more than the mesh itself. So what we're going to do now is we have these lines that are copied directly to the window, and we're going to do a sweep. By default, mine is set to round tube. Just set it to ribbon, and these happen to be pointing in the right way. Usually they don't. Let's actually crank this. Yeah, see, they're all like jank now. And that's due to the orientation. So you can lay down a orient along curve and it doesn't fix it. So we can try making the target up vector be y, and that may fix it. Sometimes it doesn't. But in this case, it's okay. So that's it. And then I would always cut this down to 1 to the max stretch, because sometimes it'll create like odd primitives in odd places that are like weird in orientation. So I don't like that. And then the width, you want this to be pretty high, because you need to make sure it extends within the grid. Make sure it cuts in the grid. In this case, of course, it is. So we have the lines here, and then we have our circle here. And we need to sweep our circle too. So we need to do the same thing we did here, and like that. Okay, and that's fine. And then we need to merge these two together. So I'm going to merge, and then I'm going to fuse. So they should be right on top of one another, because literally this circle is copying directly onto the lines. So they should be direct. All these points should be lining up perfectly, like 100%. So whenever you merge them together, you need them to be fused so that it's like one cohesive geometry. And you see the point number go down. That means it is working. And then when we fracture now, we set this to from solid to surface. It is now going to, should work. Exploded view. Yes, this is perfect. Okay, so that's the radial part. And now there's another part we want to do. So let's do this again, but instead of overwrite, we're going to say append. So we're going to do another layer. And let's go ahead and copy this again. Actually, I'm going to copy this and this, copy, put it down here. And let's do this, and this time let's make it bigger. Let's see what that looks like. It's way too big, okay? And what we can do is actually, we can do a few things. We can either copy this point, or we can copy this. Actually, we can actually do a tube instead of a circle. That'll make it a little bit easier. So, yeah, that works. And then we could adjust like the columns for sure, maybe the rows, and just adjust p scale. Okay. And then what we can do is, once this is copied, we can actually do copy transform and just duplicate this a few times and basically just scale it up a little bit so that we get a little bit of variation. And then what I want to do is create a connectivity class. That's fine, class. And then that's going to be inherited. And then we can say, we can do a mountain. And in here, like cool, let's do, we don't want to do anything in Z. We don't want to displace it in Z, so let's cut that off. So this is way too large. That looks much better. But right now they're all like cohesive. They're all treated as one. We want to separate that. So we have that class attribute on the point level. So we can actually, this operates on the point level too. So we can just say use vector expression and say offset plus equals, what was it? Class. And that should move all of them offset. And there we go. Now we can copy this over to here like that. And now you can see new, exploded view, and here's our circles. This is just one method, and you can cut this off if you want. This is just one method to do it. You know, you can modify if you want, and you can even make another one if you wanted. Like, we could make two of these. We could have this one be up here, and then this one, just merge these two together like that. And then when you copy it, it still works exactly the same way, but it's awesome. You can do that if you want. And this is all like how you can customize it, right? So do this maybe we want it way out here, and then probably want to increase the rows and maybe the columns. And yeah, that looks pretty cool. And this is all completely custom, like our way of doing things. And now all these folks are the exact same width. And you know, your client may come back and be like, hey, actually, let's tweak this a little bit. We can just change the normals on here. So right now they're all facing exactly unidirectional, and we can just modify that. So I like to say, actually depends which, okay, so none in Z. So we want to spread it, but none in Z. So we'll say direction only, spread, and we can do constant, but probably more like random, and make sure that's influencing in. And now when we do this, you can see that it is randomizing the direction quite a bit, right? You don't want to do too much because then you start getting like overlap, which is okay. But when it comes to our arcs that we're going to create later, you can't have overlapping primitives because it's going to go to the wrong one. So you want to make sure you don't do it too much. So it is a little bit more limited in that way, at least in the way that I'm doing the arcs at least. So something like that should do it. Oh, and make sure it's not doing it in Z again. And again, like if you have a slanted window or something, all of this can happen, and then you would just need to like copy this whole thing to your window. That'll be definitely the easiest thing to do rather than trying to like structure this normal like orientation stuff. It would be a lot easier just to like do everything in this space and then just copy it over to the window if it's slanted. Okay, so that's that. We have our circles, and that's that. Awesome. I want to focus on this part though. I want to focus on these lines here, okay? The lines in between. How do we do that? So how do we make arcs that are circular in between? So before I get started, there's a disconnect in the video that I want to address. Whenever you're copying to the points here, you want to resample by a huge amount so that whenever you fuse, it lines up perfectly. And then you want to create a group for your lines called line points so that whenever we eventually create our arcs here, when you merge them together, you can fuse them one to one and they'll just line up. So we fuse, it connects to the nearest point in position space. So I've created a arc group here for my arcs. Again, this is in the future. We're going to do this in the future. And then this is my line points. And when you merge these two together, you have a fuse. The target group is line points because we want to merge from the arcs to the line points. And then we're saying just closest target point so that it ensures that it's actually the closest. So that's really important as well. And yeah, so this should definitely help with the disconnect in the video you're about to see. So yeah, we're going to create our own lines. So let me move this out of the way. Move this out of the way. Right. All right, let's do it. So we're going to leave this here, leave this here. Everything else is correct. We just need the arcs. So let's do that. How are we going to do the arcs? Let's move this up here. And this, we'll add a null so it cancels that group looking at. I don't like that. So, all right, let me make a quick wrangle here to show you what needs to happen. So essentially what we want, still doing it. Essentially what we want is still doing it. Essentially what we want is we need a way to accurately create a circle here. Let me bring up my Epic pen. So we need a arc that starts from here and ends directly right here, right? And then we might want to do it again, another arc here to here, and ends exactly right here. And we needed a way to compute that mathematically, right? So we need a way to scatter some points. Let me go ahead and show you the theory here. We want a way to scatter some points. Let's template this. So we want a way to take, say, like this point here, and rotate it from its current position over to here, exactly where it should be. And then same thing from over here to over to here, exactly where it should be on this primitive. And then the tricky part that I'm going to address later is getting it to over here. Again, like another arc. And we're basically, I'm going to make a tool that'll define how many arcs we want and make that, and that'll be a per point attribute. So maybe this point gets 1 arc and this point might get 3 arcs. And maybe this part gets 6 arcs, so it goes all the way around to here maybe, and etc. And now the trickiest part is going to be how to make multiple arcs, but I'll get to that later. The first step is just to figure out how do we rotate from this point to this point. What does that require? How do we rotate a point? And I'm going to break down all the components of how to do that. So first off, let me clear this. First off, what is a rotation? A rotation is simply, well, just that. We need to define where it's rotating from. So we need a rotation point. Now, by default, of course, when you do a transform, this pivot is at world origin 0, 0, 0. If I were to rotate this in Z, it's going to move it all over the place, right? It's going to move it from that origin. Now, what you could do is you could say, okay, well, let's actually rotate this by CEX. And let's rotate this in Z like that, right? Well, we had to move the pivot to this location, but we need a pivot like per point. This CEX is our impact point, is the very center of where these lines are coming from. So that's not hard. We already have that. That's right here. This is our pivot. This guy is going to be our pivot, right? So let's start rotating. Let's figure out how to rotate a point. What do we need? The simplest form of a rotation is a quaternion or a matrix 3. I'm mostly used to matrices, so I may convert it to a matrix, but a quaternion, let's break it down. We need an angle and we need an axis. So an angle, so you see here, returns a vector 4 and it defines a specific rotation. So quaternion, you can feed it either a matrix 3, which already exists, and this is just a way to convert it, or we can define our own here, or we can have our own. So this one right here, this third option, is the most similar to a transform node. This is the angle axis. So if you do an angle axis and you basically convert it from rank, I'll show you actually. Let's make a orient equals quaternion, and we can say angle axis. Now we'll do this. I'll show you what this does. Now if I turn on this, we can actually see the orientation. We have this. Now let's go ahead and rotate it. Well, that does it wrong, but if we rotate this in say 1, it's too much. Like this is already too much. This isn't behaving how I want. Like I need it in degrees. So by default, this is in radians. So we're feeding it in what we think is degrees, but we need it in, this needs radians. So we're going to say radians. So this is going to convert what we have as an input and put it into radians. So now if I say 45 degrees, you'll see it's now rotated exactly 45 degrees, right? All right, so that's that. So we have our orientation, and this is just the orient though. If we want to actually rotate a point, we need to take this quaternion and actually we'll rotate it, right? So I'm just going to say vector 4 q. This is going to be a non-attribute thing. And then what I'm going to say is just v at p is equal to q rotate. It needs a quaternion and it needs a vector. So we're going to say q and p. This is literally going to do the exact same thing as rotating everything in transform space in 60. So if I say 60, should be the exact same thing. See? Awesome. You can also convert this into a matrix. This is usually how I work. So I'm going to say matrix 3 is equals to convert. It converts a quaternion into a matrix. So we're going to say Q. And we need to actually label this attribute. And by default, it's not going to do anything, right? Because we haven't applied anything. But so instead of VIP equals Q rotate, we can do this a different way. We can say VIP times equals M. That's the way I like to work. It's like the simplest, but then you have to convert it into a matrix, which you may not want to do. That's perfectly fine. You can do either one. All right, so we figured out how to rotate the points. But the problem is all these points are moving in world space. We need to affect only locally based on where the pivot point is. Well, how do we do that? Well, similar to how the transform works, we needed to say grab the CEX and that resets the pivot, right? And then when we rotate by 60, it rotates it quote unquote locally according to that pivot. Well, how do we do the same thing here? Well, we could do it with an actual matrix, but that's kind of complicated and I'd rather just not do that. This is a very simple situation, so I want to keep it simple, right? So what we'll do is we'll just keep our impact point here. We'll plug it into the second input. And what I'll do is I'll just say, instead of rotating it now, what I'll do first is I'll create my quaternion, that's fine. I'll make a separate attribute called pose, and I'll make it equal to P. And then what I'll do is first, I'll do this and set this to pose. So this isn't going to do anything, right? It's not going to do anything at all. It looks exactly the same because we haven't done anything yet. Pose is equal to position, but we basically want to move it to the world origin area. How do we do that? To reset the world origin, what we need is we need that pivot. So we're going to take this point and we're going to use that information as the pivot. So we're going to say vector pivot is equal to 0.1. We're going to get that first point data. It's only one point, right? It's just one single point, and it contains that P. And we're going to use that as the pivot. We're going to store that as a pivot variable, right? Grabbing the first input, the position, and the first point number. Now what we can do is say pose equals pose minus pivot, right? Let me show you what that does. We can also say, as a shorthand for this, we can also say pose minus equals pivot. Now let me show you what that does. If I say P is equal to pose, first let me disable this. You can see what it did. It actually moved it to the world origin, right? It's the same thing as this, except we're kind of doing it in reverse. Instead of resetting our pivot, we're taking the points down to world origin, and then we're going to rotate it. Let's do that. And then let's put it back. So once we rotate it, because this is all happening in world space, so we need a way to either move the pivot, move the points down to world space, and then put it back. So that's what we're going to do. Or you can figure out how to do the pivot in matrix space, which I don't want to do again. So let's put the pose back. So essentially before, and then after. This is the same thing. The reason this is different is because this is taking the bounding box information and not the explicit impact point. This is technically the absolute center. So now when we look at this template, we can see that whenever we rotate this, it actually will rotate with according to our pivot, right? So this is great. This is a wonderful, wonderful start, right? Okay, well, what's the next step? Well, essentially we can treat each of these lines as an actual vector. So this line can have something called a tangent u, which describes where it's pointing towards in space. If I lay down a polyframe node and I set this to tangent u, let me see what's going on here, why we're seeing this. Okay, let's look at this tangent u, and if I crank this up, say like 10, let's actually look at this. So these are pointing inward because I have my tangent u, have my show tips on. I can see where they're actually pointing. This is okay, I guess. But you can actually reverse this. It's fine. You can just reverse this, and now they'll point the other way, right? So either way, so each point now has a tangent u, which is great. Now we can use that information to figure out how it should rotate. So now that each point has its own, I'm actually going to move this over here, and I'm going to move these points here. So let me just cancel this. Okay, so this point has a tangent u, and essentially we've rotated all the points according to their, let me see what this does. Hang on. Yeah, so the tangent u is not moving. It's only the position, right? And we would expect that because, again, you have to be very explicit. We could actually rotate the pivot as well. So we could say the at tangent u equals q rotate, q tangent u, and then that would also rotate the tangent if you want, right? And now it's rotating, right? You could do that. We don't need that to happen. In fact, we don't want that to happen. So we have the rotation figured out. Now what do we need? Okay, well, so we need to get what is the angle between this vector and this vector, right? Let me draw my pen. So this vector here and this vector. What is this angle here? Like theta, right? What is the angle between these two vectors? How do we get that? Well, first let's start with baby steps. First, we need to define what the next vector is, sort of quote unquote. What is the next vector? Well, it's the vector to our right, probably. Okay, well, what is that? So we need to define, actually here, I'm gonna do this style. I like this style a little bit better. So here I'm actually going to define what's called a polyframe. So a polyframe will calculate the tangent of the primitives, and they are currently reversed, so I'm going to reverse this. So interesting, it actually moves the points. Interesting. Either way, so we want them pointing out. So this gives us a tangent u, which is very helpful for down here. Now we need to define some information on the primitives. We need to tell the point which primitive to actually go to. We can do that by storing an attribute on the point and then later on the primitives. We can say, well, let's get the primitive. What is the primitive? The prim is prim num. Okay. And now you can see 0 is prim. Oh, sorry. It stores which primitive number it came from. So this particular point, let's see. This particular point came from prim 12. So if I look at this primitive came from prim 12. Not quite working. There we go. Prim 12, see? So it all works. Great, so that's on the primitive level, which is fine, but we need the next primitive. What is the next primitive? How do we get that? So the next primitive is going to be defined with this. What we can do is actually, we're going to convert to make my life easier. We're actually going to come down here, and in this branch, we're going to convert some of these attributes to primitive just to make my life easier, so we don't have to do some of the math that I did earlier. We're going to convert tangent u, and we're going to convert what's called next. We're going to do that later. So next is going to be next. First, let me just make sure this works. Okay. Yeah, it does. Okay, great. So next is, what is the next primitive? So we have prim equals prim num, but now we want int next is equal to the prim, or other prim, plus equals 1, or plus 1, right? So each primitive they're sorted in a particular way. So right now they're sorted in a clockwise position. So 12 is now going to look at 13. 14 is going to look at 0. 0 is going to look at 1. 1 is going to look at 2, etc. So next is prim plus 1. And don't worry, we're going to fix number 14. That's next, because we want to say, well, if the primitive is equal to the number of primitives. So here's what we'll say. We'll say if prim is equal to n primitives 0, then next is equal to 0. And then we'll say next equals, next is equal to next. So here's what's going on. If the primitive number is equal to the number of primitives, so if the primitive number is equal to 14, so if it's equal to 14, then our next is actually going to be 0. So this way 0 will look at 1 will look at 2, 14 will look at 0, etc. So this is how we fix that error where 14 is not going to have anything to look at if you're just adding 1 to it, right? This is the error fix, right? So 14 is now going to look at 0. So if we look at next, if I make it new marker, we can call it next. It's on the primitive level. Let me turn this on. We cut this off, call this next, right? We cannot see it for some reason. Why can I not see it? Doesn't want to show it to me. Oh, because it's not converted yet. Okay, there we go. So now the next is 15. Well, that's not correct. That is not correct. 14012. Okay, that should be correct. Let me make sure this is correct. This is primitive number 14, and it is looking at 0. I look at 14, and it is looking at 0. 0 is looking at 1. 1 is looking at 2. This is correct. Okay, great. So great, we have the next primitive. Now this is going to be really useful later. So we have our tangent u, and we have our next. So let's actually look at the tangent u again. To make sure this is correct. Now I should be looking at the primitive level, and I guess because we can't actually see it on the primitive level, but it is there. If I look at the primitive, cut this off, you can see that the tangent u is actually there, and we have our next. Okay, so this is really going to be really helpful later. So these points also have tangent u and the next. Should have next anyway. Yes, they do. They have the primitive number and they have the next, which primitive they should look at, right? Great. So we have our bare bones like system here, but we need to modify it to actually correctly rotate. So the way we're going to do that is this tangent, we cut this, oh, it's off already. This, again, we're going to treat this as vector math. So we're going to say, what is the angle between primitive 13 and 14? What is the angle? How do you get the angle between two different? Well, first we need to get the information we need. So first, let's cancel. First, let's get our pivot. This is the wrong pivot. We need to say 2 here, right? And now we rotate. It works correctly, right? Okay, so great. This Q needs to be adjusted later. I'm actually gonna go ahead and delete this angle axis. Now that we know kind of what we're talking about here, we don't need this anymore. So yes, I know. This is just to show you kind of how to do it, right? Okay, we have our pose, we have our pivot. That's it so far, right? So what do we need? Oh, we also want an index because we're essentially what we're going to do is we're going to create points along as it rotates, right? So as this point moves along, we're actually going to create points along that trajectory. So what do we need for that? Well, first we're going to get our next attribute. So next is going to be next, right? We already have that. And the prim is going to be, well, prim. We already have that too. And we can modify these later. But for now, let's do this. So first, let's go ahead and just add a new point. How do we do that? Well, we say add point is 0. And we can give it a point number to actually add to, or we can give it a position. So we can just do that now. So I can see our points actually doubled. You don't see a difference, but if I just lay down a point jitter, you can see we definitely have more points now. Let's scale it in just to show you we've definitely added more points. You can see before, after, right? Each point has a new point now. Okay, so we've added a new point, and that's the gist of it. So when we actually move this point in space, we're gonna need to add a new point each time, and this point's actually gonna move. So let's go ahead and we need to also set an index. So we need to enumerate this, and this will just create like an ID for each point. So we can just say index. We can just call it index if we want. Yeah, right. So index is equal to index. All right, on this new point, we want to set point attribute. So what we're trying to do now is say, okay, for this new point, we're gonna set its index to whatever that index was before, so that the attributes are correct. Because essentially what we're gonna do is we're gonna come down here after all this is said and done, and we're gonna come down here to group, and we're gonna say index here. So both the new point and because if we do this now, we should do point jitter, and scale it in. This isn't going to work because they're different indices. So we need to say set point attribute 0 for which geometry is it? We're looping over the index. We're going to set it on the new point, and then we're going to set index to be that. And then we're going to say set. So what do we want to do with it? Set. Okay, so now we have primitives between the 2 points. So we have this point, these points here, and then we're moving them out a little bit, and then we're adding. So instead of this jitter, obviously we're going to rotate the points, but you get the idea. This is essentially what we're going to try to do, right? At the very end, when we create our curves, we're going to reconstruct a primitive according to this methodology, right? Having that index. This index is very, very important. And that's really the only time we need to set this index. This time and another time, but that's it. Set the attribute, that's it. Because that's the most vital part of this. We don't need really anything else. We just need this index. So we've set the index. And again, I'm getting kind of ahead of myself a little bit here because I have my notes right here. But I'm just trying to get through this here. So we want to get, okay, well, we have our tangent, our current tangent, right? We have that already. We need to get what the next tangent is, because basically we need to get, like, let's say the point is here. Let's say the point is here. We already have its tangent, but we need to get this primitive's tangent here. Oh, I need to make a very important point. All of this assumes that your lines are not noised up. This method that I'm showing you right now is not going to work if the lines are noised up in space. We need to make sure that, because if your lines are noised up in space, this tangent u is obviously going to be changing every single point. If I noise this up with a mountain, obviously the tangent is not going to work anymore because now the vector changes for every single point, right? The tangent, if we recalculate the tangent, let me show you. If we recalculate this tangent, every single point is now different. And there's no way to explicitly get a correct point within that circle radius unless you explicitly do like a feedback loop to figure out which point it should be. So that's why it's super important to make sure that the tangent u is a straight vector, so that's extremely consistent. That's super important. You can always noise it up after we do this method, but just make sure that your points are not noised up for these lines. They have to be consistent to correctly do the vector math, right? Okay, so we have that index. So what we're going to do is we're going to create our t is going to be our current tangent, and this is going to be just tangent in this case, right? And we also need nt. So nt is going to be what is the next tangent. Well, for that, what is nt? Well, we need to get the next tangent. So let me write some notes out here. First, get the next primitive. Okay, we're done. We're done with that. We already have that. Next, get the tangent u of the next primitive. Quat, angle, axis. So we need angle and axis. So we need angle between v1, vector 1, or tangent 1, or just tangent, and nt. What is the angle and what is the axis? We need to calculate those two things. We need to calculate the angle, we need to calculate the axis, right? Okay, so how do we get the angle between two vectors? Well, first let's focus on getting this actual nt. What is this nt? Well, we already stored the next primitive. That's 3. We can just use that. We actually already wrote it down here. Next is next. So we can just say prim. We're actually going to look at, so we're going to use this point information, yes, but we're actually going to look at the primitive information on these points as we go. So we're going to say nt is equal to prim. What is the primitive information? Get a primitive attribute from a geometry. We're going to look at the first input, or sorry, the second input, technically. And we're going to say, well, we need the tangent u of that primitive. And then we're going to say next for what is the next tangent. Let me show you how this works. Nt. So we have our tangent u, and we're going to say, well, what is the vector of the next primitive? So this vector here is suddenly going to look like this vector. And then this vector is going to look like this vector when we run this. Ready? Well, it didn't actually move, but you see my drift. Like now this vector is pointing in exactly this direction, and this vector is pointing in exactly this direction. So you see what we did? So we're getting the next tangent over. What is the next tangent? Now we need to get the difference between these two. We need to get the difference between this vector and the vector you just saw. We need to get the angle in between them. Well, how do we do that? Well, you can just look up how to get the angle between two vectors, but this is essentially what it is. It is the angle between two vectors is the arc cosine, or a cos, like arc cosine, inverse cosine of the dot product between t and nt. Okay, that's the angle, and this is returned in radians. So if we look at this, angle is equal to angle. You can see each angle is slightly different. If I cut this spread off, each angle should be pretty much like identical. Yeah, 41, 41, 41, 41, right? All right. Just to show you that it is working, okay? We're getting the angle, and this is in radians. If you want, we can say degrees is equal to, or angle degrees is equal to degrees angle, because again, this gets returned in radians. So you can see, okay, we have the angle, and now we need the axis. Well, the axis to rotate from is actually just this one, right? It's just this axis, or this one. It's the z-axis in this case, right? But let's say we didn't know that. Oh shoot, I did not mean to do that. Let me trash this. Let's say we didn't know what the angle was, so or what the axis was. So in this case, it is just z, and it's as simple as that. But let's say we didn't know. This is just a good opportunity to teach vector math here. So the way you find out what the axis should be is something called a cross product. A cross product is actually shown right in front of you, this x and z, or y. So the cross product between this x component, x vector, and the y vector is the z vector. And the same is to be said about the y component and the z component. They're all cross products of each other. So if you do the cross between z and y, you're going to get the x axis. It's what is the perpendicular vector between two sets of vectors? What is the perpendicular vector? So what is the cross product between this vector and this vector? It is this vector pointing directly away from you. What is the, let me clear that. What is the cross product between this vector and this vector? Well, a vector again pointing perpendicular to those two vectors. This is how you get the axis to rotate around, is you do the cross product between so like another good example is what I've done for spinning debris is I've set the spinning rotation value to be the cross product between the velocity vector and the up vector. And that'll get you the exact rotation value needed to rotate your pieces correctly, right? So the cross product is extremely useful, and it's used in so many different things. So that's why I wanted to show you guys. So we also need the angle, or the axis, sorry, so the axis. So the axis is going to be the cross between the normal, or sorry, the tangent and the next tangent over. But this isn't quite correct. If I print this out, equals axis. You see how they're all like slightly different, and they're not like negative. It should be negative z actually, and they're all different values. And that's because the cross product has to be, in order to become it doesn't always output a correct vector. So you want to make sure to normalize it. So you have to normalize it. And now they all return -1, right? In Z, right? So just make sure that's where. And the reason we're seeing all these zeros here is because we just didn't set those on the new points. But don't worry, they're only needed for the current points, not the next ones. So we have our angle now, and we have our axis. So that's what is required to make the correct quaternion. So let's go ahead and make our quaternion now. So Q is equal to quaternion. You can just hit tab to go to the first entry. And I think you can hit tab again. No, okay. So again, we're going to use this option here, quaternion float and, or sorry, angle and axis. So we're going to say angle and axis. That's your new quaternion. Let's go ahead and do it. Let's say v at p. Actually, we're gonna, actually, yeah, let's go ahead and just do it. So v at p equals q rotate q and p. And you'll see what should happen. Oh, I forgot one super important thing. The pivot needs to be moved first. So let's go ahead and do that. Oh, also this has to be a vector 4. So here's the problem. We need to move the points to world space first, right? I forgot to do that. So we have pose here. So let's move pose. Pose. We'll say pose. Actually, let's do it here. So pose minus equals pivot. We have to remember to undo this. And then pose. We'll rotate. Pose. We have to remember to undo this part because I'm just showing you. Pose plus equals pivot. And then v at p equals pose. Okay. Now, so for, after, for, after. Then we can go ahead and actually go ahead and draw that, right? Okay. So we're one step further. We've correctly taken this point and rotated it 100% to this point, to this primitive. Awesome. We can draw a line through it and we can really be done with it. We can kind of just be done with it right there. This isn't good enough. What if the client's like, oh, actually I want 2 arcs per thing. And we're not even there yet. First, let's create the interpolating points. Now, you might be tempted just to resample, and you're right, you can do that, but that's not a circular pattern. If they want a straight pattern, fine, but if they want a circular pattern, yeah, you're kind of stuck, right? You need a circular pattern. So we need to actually, instead of rotating it all at once, we need to incrementally rotate the point and add new points as we go. So instead of doing it this resample method, we need to actually incrementally rotate and add new points as we go. So we're going to add a point here, 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 here to create that circular fashion. Okay. Okay. So how do we do that? First, before I make a mistake, I'm going to get rid of this because we actually don't want this. I'm just showing you how to do it. We've made our axis, we've made our quaternion. Now we need to do something slightly different. This axis, and really it's best to normalize these two vectors. So normalize, just to make sure that the cross product does actually come out correctly, right? All right. So what we need to do is incrementally add new points. So the way we're going to do that is with this. We're going to say, first off, this quaternion needs to be manipulated later. So we're going to say, actually, I'm going to put this up here because this is very distracting. Put this up here. And this can actually no, we're going to leave this here just in case. We need to make several points. So we need a way to define how many points we want in between. So do we want 6 points in between or 8 points? Let's do that with a channel. Let's call this channel num points. So num points. How many points do we want in between? Let's see, count. Let's go ahead and make this like 6. So we're going to have 6 points created in between to create that arc. Okay. And then we're going to say we have that. Actually, let's move this up here. This is a global variable we can just set. Let's move actually way up here. As a global variable. Okay, but this guy is going to change. So is the axis. We don't even modify that yet. But this quad is going to change, so we're going to modify it here. So let's do this now. So we need to figure out, okay, well, how do we define how much to rotate by for each point? How do we add 6 points? Well, we need a for loop. It's called a for loop. So we're going to say for int I is equal to 0. And then you say I is less than the count. So what do we call it? Num points. So copy that. Num points. And then we're going to say I plus plus. So this is a very basic like for loop, how you do a for loop. So we need to add our points in here. So we can let's go ahead and say add point and then, like that. That this is essentially the gist of what we're trying to do, right? But we need to increment this angle by a certain amount. So the angle needs to be incremented like this. So we need to say angle inc for our increment equals the angle divided by the num points, right? So the angle, if you divide that angle amount by 6, you're going to get the correct angle each point needs to create that next point. The increment angle, if you divide it by 6, because we're going to create 6 points, you divide the total angle that is required by 6, you're going to get each incremental step of an angle that is required to create that angle. So let me go ahead and just show you what this is going to do. So we've created the angle increment, and now we can do what we did here, but instead of Q, I'm going to modify Q actually up here. Actually, wait, this needs to go up here. We're just going to create a new quaternion, it's fine. So Q is actually going to be quaternion, the angle inc by the axis. This is our new quaternion. It doesn't matter if you reset it as long as you're not adding to it or whatever. This is completely resetting it, right? So Q is this, and we're going to take pose that we created earlier. So we're going to say pose minus equal pivot again so that we can normalize it. We're going to Q rotate pose. Sorry, Q rotate Q pose. And then we're going to add it back to the pivot. And then we're going to add point. So add point 0 pose. Let's see what happens. See what happens? So now we've actually done it. In this for loop, we've created a quaternion that rotates the point, the current point, or it will rotate it. We've subtracted by the pivot, we've Q rotated it, and then we've added it back to the pivot. This is just like how to negate the world space problem. And then we're adding that point back, right? And this works. This is awesome. We've created a arc, and now if we check this, it breaks. And that's because we're not quite done. There's issues with this. We need to set this attribute here like this. And we're going to call this new PT is this, and that should fix that. There we go. That fixed it. Awesome. So now we've made, and then you can even set this to subdivide to really like subdivide it, right? This is essentially our arc. We did a great job. So we've made one arc, but what about more arcs? What if we want more? Oh, also we need to fuse this to make sure there's not like multiple. Yeah. Okay. So we've done it. We've created an arc creator, right? But now the problem comes, well, what if I want multiple arcs? So this is where it gets definitely more complicated. We've already done this math. Let's call this rotate. We've already done this math, but we need to do it multiple times. Okay, so now we've created our arc creator, but now the issue is, well, we want to create multiple arcs per point, and we can even vary how many arcs we make per point. But the gist is we want to make multiple of these per point potentially. So we need a way to because each one of these primitives has a different tangent u. So we need to update the tangent u and the new tangent vectors as we go. So as soon as this point here has reached this point, we need to say, well, what is the next? Let me just write it out here. Once we have reached new primitive, what is the next primitive I need to look at? What is the current tangent u of the current primitive I am on? What is the next tangent u of the next primitive I want to go to? That's what we need to figure out. Once we've reached the new primitive, what is the next primitive I need to look at? What is the current tangent u of the current primitive I am on? So if it's moved from this point to this point, what is this current tangent? And then what is the next tangent? What is this value? Okay, that's what we need. We need to figure all that information out. All right, so what's next? So we actually wrote the next primitive on an attribute for a reason, because I knew I needed a way to actually look up this information once I reached a new primitive. That's actually why we wrote next as a new primitive instead of just storing it once on the points and that being that. I knew I needed a way to access this information as I went. So that's why we made an attribute for it here on the primitive level. And in my original, when I first created this, it was actually at the point level, and I switched to a primitive method because it's a lot easier. Because otherwise you would have to say, instead of just using a very simple prim, you would have to do this. This is what I wrote out before, is I said, okay, well, what is the prim points? Prim num, just to show you. Prim num, and then what is the first point of that primitive? This is what I did, right? Basically, well, this, and then tangent u, and then this. This is what I had to do every time I wanted to look up an attribute. And this was annoying, to write 2 lines of code instead of just one, instead of just a very simple prim. So let's stick with that. So first, let's actually create an attribute per point that defines how many arcs we want per point. So let's go ahead and do that. Let's call it arc count. So I'll make another wrangle, and we'll say arc count is equal to fit01 random pt none, or we could say ID if you want. It doesn't matter in this particular case. We'll say min arc count and max arc count, and say let's see, I know there's a round function, int. Well, that works, but really we just want to say int, convert everything to an integer. Oh yeah, we could also seal it so it's going to the most vector. So now you're going to see each one gets a random arc between 1 to 3. Maybe we shouldn't do sealing. Maybe we should do just fitting it. So now it's 1 to 2. Actually, I don't like this method because we're not actually able to see everything. So maybe we should just add 1 to this. So now we're actually getting what we're actually looking for. It's 2, and 3, and then 4, and then 5. This is actually what I would expect, right? We can use this attribute later. We can actually use it here. Let's go ahead and grab it. So this is not going to change per point. Let's just write it in our global area because it's not going to change. So we'll just write it here. So we'll say arc count is equal to arc count. So we can use it later. I like to do this because it's a lot shorter to write just arc count instead of at arc count. It's shorter. So that's why I like storing it as variables. And then we can use it later. So what do we want? Well, we need another point number, actually. We need another for loop. So let's write another comment here. Write for loop that goes from 1 to number of arcs and iteratively gets new tangent and new next tangent per arc iteration. Okay. So here's how we're going to do that. These are all constants, and it's okay that they're here, but these can actually be updated in the for loop. So if I write something that's next here, this can actually be accessed within the for loop. So, and we can update it in the for loop. So let's actually write the information here. Let's write the new for loop here. So we can't call it the same thing as this one. So this one's actually, you know what? Let's actually make sure this is correct. 1, 2, 3, 4, 5, 6, 7. We actually have 7 points. So let's actually do this. Let me make sure this is correct. I guess because it's starting with this one, so it's creating 5 new points. Okay, yeah, actually that makes sense. Because we've already created our first point here. That's why it's not considered in this one. Okay, that makes sense. We're creating 5 new points. We're not starting from this one. It's creating 5 points after this one. So 1, 2, 3, 4, 5. Because I was worried for a second that my math was wrong, but this is fine. So the reason I changed this from a 0 to 1 and made this equals is because it actually makes it a lot easier to figure out. I mean, I'm sure if I thought about it for a second, I could figure it out, but I'm lazy, so I'm just gonna do this. Is the same thing. So if this is just like your normal counter. So like how we count on our fingers, 1, 2, 3, 4, 5. This is how it's counting now. So we're gonna do the same thing up here so we can access the last index easier. So we're gonna say for int j, we're going to say j is like another count because we already have I, so we have to make a new temporary variable that represents what is the for loop iterator. So we're going to call it j, and again, because we already used I, so we have to use j now. Or it could be anything. It could be y, it could be igloo, it could be anything. If j is less than arc count, and then j plus plus. So this is our new for loop. And I'm gonna, to make this cleaner, I'm gonna just tab all of this over, and then I'm gonna make a new thing. So it's actually running multiple times. That actually looks pretty cool, but it's incorrect. See, it's not actually going to the correct primitive. It's just looping multiple times. So this is kind of working, but we need a way to update the information. And this is actually very close already. So what we need to do is let's do this one. Again, we need to update it only when it reaches the last point. So as soon as it reaches this point, grab the new information. Okay, so here's how I'm going to do that. I'm going to say, since we have this index this way, it's very easy to say if I is equal to number of points. So if we say if I is equal to num points, then update the information. Okay, let's write a new comment here. We need to grab new primitive info, all new primitive info from the current primitive it is looking at. Yeah. Okay, how do we do that? Well, I'm actually going to use, you could use next. Actually, yeah, we can use next, but then we need to update next. So next is equal to prim1. Look at the primitives on the right-hand side. We need to look at the next primitive, and it's going to be next. We need to get the tangent, so we need to again look at, but we also need the tangent u, and next. And then we need the new tangent. Now the new tangent is different. The new tangent is not going to be nt1 tangent u. No, first we have to get what is the next primitive. Oh, actually we already have that. Actually, let's do this. We already have that. That should have been this. New next. This is next. Then this is new next. New next. Okay. And then our next needs to be updated to new next. And now that works. So essentially, we are saying, looking at the next attribute or the next variable on this point, grab the next attribute using the next as a reference. So next is the next primitive, and prim is the current primitive that it was on. Next is what it's looking at. If we grab this is a reference. So, and this is the attribute or variable we're using to say, well, what is my next? So new next, or what attribute do we want? And then this is what are we going to use to look at what indexes should it be? What attribute are we looking from? Well, what attribute we are looking from is this primitive. So we're trying to say, well, what is this? It's next. So if this, let's say this is 10 and this is 9 and this is 11, let's say. This new next is going to be, if this is 10, then this would be 11. This would be return 11 as its new next. And then t prim tangent u next is saying, what is this tangent here? Let me draw this. What is this tangent here? Give me that. And then nt prim tangent u new next is, we're on this tangent. what is this tangent? That's nt. And then next is new next is just saying this primitive, not this one, new next. That's that. So the whole reason that this can work is because information that you update at the bottom of a for loop goes back to the top of the for loop as that new value. So when we say next equals new next at the end of this for loop, it goes to start at this for loop at the next iteration as that new next. And so when this runs, next is now that new next. So let me demonstrate. If I have, let's make a integer called f and make it set to 1. And I'm going to make just like a random, let's make this 1, and then I is less than, say, like 5, and then I plus plus. Just to quickly show you, I don't want to digress too much because I might forget what I'm doing, but I is the temporary variable assigned to the index that's going to be running over. I is less than 5 is the condition. So you say you have your identifier part of the for loop, semicolon, the condition that runs, I less than 5. And then what is I going to be doing during the entire time? Well, I is plus plussing. So I is plus equals 1. So at every iteration, I want you to increase I by 1. That's what the plus plus is short for I equals 1. So if we update f, we say f plus equals 1, then f is actually going to end up being 5 or 6 at the end. Wait, say 1, 5. If 1 to 5, it'll end up being 5, 6. Should be 6. So if I say f equals f, should be 6. Oh, it's 5. Oh, minus equals. There we go. That should be 6. There we go. F, this is called a global variable because it lives on the outskirts of any for loop or while loop or anything else that we have up here. And then this is the for loop, and this is called a scope. So as you can see, anything that runs within this for loop gets updated. Now let me go one step further. Let's do another for loop. Int I equals j equals 1. J is less than, say, like 2. Then we want to say j plus 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 plus. Now this for loop, I want to say f times 2. Now it's going to be a huge number because this happens more than once. So actually, let's just do that. Actually, it's okay. We can just, it still proves the point that f is being updated here. So it runs like this. It reads top down. First this happens, then it reads, oh, this is a for loop. Okay, I'm going to run this however many times I need to. So in this case, it's 1, 2, 3, 4, 5. 5 times. I'm going to run this 5 times. 1, 2, 3, 4, 5. But during that time, there's another for loop that runs twice. So first this runs one iteration. So it goes to here, it reads this, it says, okay, I read this. Okay, this is a for loop. So here's my first iteration. Okay, f plus equals 1. And then it reads that there's another for loop, and it goes, oh, wait a minute, I need to do this twice. So then it says, oh, okay, this is my other block. Run this twice. So 1, 2. Then at the end of this, it goes back from this, and it goes to this line. Of course, there's nothing there, so nothing happens. So then it goes back. Let me show you that. So then it goes back up top. It says, okay, let me go. I'm not done with all my for loops. I have 4 more to go. Let me go back up to the very top and start over. So now I run this again. What happens here? F plus equals 1. Oh, there's another for loop. Okay, 1, 2. And then there's nothing here at this line. And then again, I'm going to go back to this line. So that's how that works. And that's how for loops work. Nested for loops anyway. Like I said, this is just to demonstrate anything that gets updated in here. So this global variable will be updated in here and referenced in here. And then at the end of this iteration, f is now returned on this line. F is now whatever this is, say like 16, and then it's saying 16 plus equals 1. If this wasn't here, f would end up being 5, or 6 actually, because it starts at 1. But because this is here, f constantly gets updated within this for loop as well. And so that's why this whole system works, is because we can take what's here, feed into the for loop. First off, that's one condition that allows this to work. And the second condition that allows us to work is being able to update that variable within another for loop. So what we're saying in our course is we're saying at the end of this loop, update f. We're not doing it before or during the whole for loop. We're only doing it at the very, very end. And that's how that's working. Let me get rid of this. I showed you that. Because we're saying at the end, when I is equal to the number of points. So basically, when we're done with that very first arc, then update all the variables. So as soon as it gets here, update all the variables, and then go down here. That's how that works. Now the arcs are all created, and we can fuse them if we need to, and we can resample. Everything works. All right, so now what we need to do, let's just merge this and this. And now they're one-to-one exactly where they should be. And let's disable this for now. I don't want to resample anything until I fuse. We don't need this anymore, but we do want to create a group for this. We're going to call this arcs. And then here we're just going to say, instead of fuse, we want to fuse all the points to the lines like this. That should be pretty, I mean, they should already be pretty much like straightforward. Oh, I forgot I did that. I made a, just so I could see it in my viewport. There we go. Yeah, that's what I'm talking about. There we go. Okay, so we've successfully created that. And then if we do polypath, oriental on curve. Actually, after we do this, fuse and polypath is for when you want to successfully rewire all. I mean, you typically do it after a fuse to make sure all your primitives are correct. They're separated out into the correct primitives. Like this is this. Otherwise, yeah, see, like it might be a different primitive. And so the polypath ensures that if it's connected to a different neighbor, that it's going to be the correct primitive. It's going to separate it out correctly. And then we can say oriental on curve and sweep. And that's it. And then let's make sure this is all correct. Fuse to fuse everything together. And then exploded view. All right, so we have successfully built a totally customizable window fracturer. And what you would need to do after this is you would need to do like an attribute noise after the fact. And you would not do it along Z. And you would say P here. And you would make sure that this is 0 centered. And just make sure this is negative, negative, negative 1. So maybe like that might be good, or maybe like that, and down this size by a lot. That might be a little too much. Let's say something like that. This time is still a little too much. Something like that. And then when you fuse them together, actually, you want to do this after the fact because you want to make sure not to interfere with these guys fusing correctly. But you can do it after the fact. And then you can do this. And it may or may not look correct. Now, I get this a lot, these added points. You just say, for that, you just say remove unused points, and that's it. This is how you can create. Now, if you're getting like these small chunks, that's just because it's noised up a little too frequent. So just increase the frequency, and that should help some. But yeah, that's how you can create completely custom window fracture. So that's it. We did it. This is our rotate points. This is our arc count. And then after this, you can do your regular circle fracture. This is how you can do it. And we can create more arcs. So let's say Client comes back and says, oh, actually I want 3 to 8 arcs on each one, or 9 arcs, whatever. No problem. No problem at all, boss. No problem. And you just do that, and it's done. It won't work every single time. Like, obviously, the Boolean's very finicky, but you might have to like randomize some things, maybe like change how it's scattering, or maybe change like the amount of scatter points or whatever. But it should work in general. And you may also need to play with your noise. Like this noise offset might need to be changed, so you can play with this offset here. That would help too with if there's issues with your fracture. But in general, this should work. And this is how we essentially recreated the this RBD material fracture set to glass. Set glass. Essentially how we made it ourselves, and we made it more robust. Like, this is cool, but they're straight patterns. They're not. And and if you want it to be straight, if you need it to be straight, I mean, you don't even have to do this. You could kind of just do this, fuse it, and then just, you already have your arcs, so you could just say resample your arcs, and it doesn't like it because it needs to be promoted to a group. You could group promote arcs to primitives, and then resample arcs, say 2. And this way they are lines instead of whatever they were before. This is after we fused? Yeah. This looks really bad. I did not think this would work this way. It doesn't seem to like it. Maybe I need to do polypath before? Ah, yes. I need to do polypath before. Arcs, fuse. So fuse gives me... Ah, that's why it didn't work. Because it's like, oh, I'm just going to resample this whole thing. And polypath ensures that it's divided into the correct chunks. Okay, so that's why it wasn't working. And then when we resample the one, now you get those like that spider web look. Actually, looks pretty cool. It's kind of like a spider web. Yeah, so it's all up to the client, like whatever you want to do. If you want it to be straight, you can. If you don't want it to be straight, you can also do that. What I've also done is I've taken the distance from the crack point. Let me show you what that looks like. So I've taken this, copy, and this, and then I've done mask from geo, create a mask from here to here. Let's do mask so you can see it. I'm going to cut this off, cut it way down. Oh, this is such primitives, that's why. So like this, let's invert it. Okay. So now, okay, I don't like this because this needs to happen on the line level and not on the sweep level. So because it's going to be fading on the z-axis, so we need to do this. Let's do all this at once. So let's do this and this, this, like this, and this. Just combine the curves together so that we can do this. And then sweep so that everything's uniform. Nope, we need to do the fuse before and then sweep. Oh, that's wrong. That's okay. I think it should work either way. It's just going to be fusing multiple points instead of just one set of points. And we do this. Let's see. Does that change anything? Yes, it does. Wow. Actually changed a little. Oh. No, we need to do this before. We just need to set the orient along curve again, because I guess the fuse messes every... Oh, let's not do that. Oh, yeah. There we go. Just don't recompute the normals. And then do that. And then Boolean. Is that correct? I guess. I mean, it looks okay to me. You get a little bit of points, but it's okay. This is another method. Just to make sure you get that fade out. Oh, I didn't even implement it. Okay, let's implement it. So blend shapes, this to this, this to this. You want to base it on mask, and well, yeah. And I am realizing that this orient is wrong, and that's because of this fuse. Yeah, but we need it to be correct. Doesn't like it doesn't like fusing these together and then sweeping everything all at once. Could do this mask multiple different times to fix this issue and kind of like undo it and basically redo what we did, or we can just try to fix the orientation here. Don't worry. That seems to have fixed it. Yeah, that seems to, well, we're getting this error here. I do not like this node. I don't like this node at all. If I don't fuse, it looks bad. If I do fuse, it looks bad. Okay, I'm gonna delete this. We're gonna make our own orient. Orient is equal to quads. Link transform Z Y. Let's just see what happens. So Z1, nope, wrong. 1, nope, wrong. This way? Yes, that looks to be correct. Yep. Good old fashioned math. Guess and trial and error. Yeah, I don't know what this node does and why it doesn't seem to want to work all the time, but like this part was problematic. Let's see if this fixes it. Yeah, it fixes it. I don't know what that node does, so let's just set it normal. Okay. Tangent, there we go. And there we go. And then now it's only gonna noise up, it's not gonna noise up that area. And this is just something you can play with. And you can also say scale and do it like that if you want. If you need less noise in a certain area or more noise. We can do even more now. We can maybe say like 0.2 and maybe add another one. Oh, maybe a larger frequency. Might need like 0.5 as a frequency. You get my idea. We're basically noising it all up. And then I would actually, instead of using this mask, I would actually recreate another like ramp. So I would say remap mask, and then I would like make this maybe like a B spline or something. Let's just see what happens when I do this. So less, we want more noise there, and then something like that. You get my idea. Um, let me move this up. And yeah, and then there you go. And now you get these circles. This is a completely customizable window. And yeah, so we've made our own glass fracture with custom math to do the correct arcs and everything. So I hope you've enjoyed this tutorial and really hope it was helpful. Leave a comment, that helps a lot. I like to see interaction from my audience. If you found this helpful, just leave a comment saying so or ask questions. I love seeing you guys interact with my channel. So and if you haven't already, hit the like button and subscribe. I get annoyed at people saying that, but I'm realizing you kind of need to sometimes. But yeah, I hope you guys having a great week, and I'll talk to you guys soon. All right, bye.